Hello, I'm Aki Hongo from Kono University in Japan. The co-author is Naoya Nita. Today, I will talk about towards the dynamic visualization of complex reverse engineered object collaboration. Let's start with the background. Much effort is often spent on program comprehension tasks in the reverse engineering context, such as maintenance and reuse. To support program comprehension tasks, software visualization techniques are expected. For example, UML, such as class, sequence, and object diagrams, are frequently used. However, visualization by UML is still ineffective to reverse engineer complex behavior of realistic programs. Let's consider an example of invocation chain. This code can be represented by this sequence diagram. The object A returned from getA method is represented above this arrow in the sequence diagram. Here, please notice that the role of this object is the return value of the invocation. Next, since the object receives the message getB, it is represented as a lifeline like this. This time, this object serves as the receiver of the invocation. In this way, the way of representation of the same object can change significantly with the change of its role in interactions. We think that this is a limitation of the representation of sequence diagram. In this research, we focus on 4 roles of objects in interactions: receiver, sender, parameter, and return value. This table shows how the role of an object changes along with the program execution. Invocation chain is categorized here since the object role changes from the return value to receiver. The changes of roles between receiver and sender can be directly represented as a lifeline in sequence diagrams. The changes of roles between parameter and return value are slightly unsuitable for sequence diagrams because they are represented separately. On the other hand, the changes of roles in the light blue part, that is, between receiver or sender and parameter or return value, can be represented in quite different ways. Therefore, these parts are unsuitable for sequence diagrams. We intend to uniformly visualize all of these cases. Our research objectives are first, to propose a visualization method to directly represent collaboration in which object roles frequently change, and second, to figure out the application range of the visualization method by introducing a dynamic software matrix related to changes of object roles. In the next slide, we would like to explain our software matrix. As a dynamic complexity software matrix, we propose alternation complexity. It is the number of changes of object roles in the right blue part, that is, between parameter or return value and receiver or sender throughout the collaboration. To represent object collaboration with higher alternation complexity, we propose a visualization method. As requirements for the visualization method, first, every object is to be represented in a uniform way whichever the object role changes to. Second, the information about the set of objects that can be accessed by each object is to be represented. To satisfy the requirements, we use dynamic object graphs and an analogy of magnet and metric balls. Magnet model is a dynamic visualization model to represent changes of object roles based on animated object graphs. In magnet model, each ellipse represents an object. and the rectangle inside the ellipse represents an execution of a method. Also, solid arrow between two ellipses represents an object reference by a field. A green dashed arrow between two rectangles represents a method invocation. With respect to an animation of object returning, when object C is returned as a return value, it moves in the same direction as the return from B that gets C. With respect to animation of object passing, when object B is passed as a parameter, it moves in the same direction as the method invocation of D.passB. We implemented a visualization tool named magnitude based on magnet model. Here, we demonstrate animation of a feature of open source software by magnitude. First, open a magnitude file with information to extract feature. After reading the magnitude file, select the feature from Extract Feature menu. You can scroll to see what you want to see. Press the play button to start the animation. You can pause the animation. You can also zoom in to see the details of the diagram. Let's resume the animation. The deepest method execution in the code stack is colored in the darkest pink. In auto-tracking mode, you can track automatically the deepest method execution. If you want to see the entire structure, you can zoom out. You can fast forward the animation up to 10 times speed. Last, let me conclude my talk. First, we defined alternation complexity as a dynamic complexity matrix. By an experiment with participants, we confirmed that it captures an aspect of difficulty in comprehending collaboration, and that will be explained in the poster session. Second, we presented a dynamic visualization model named Magnet Model and implemented as a visualization tool. Future work is as follows. Now I'd like to close my presentation. Thank you very much for your attention.